Hi, my name is Breland Statham, and I will be explaining problems number 16 and 18 from Chapter 4, step by step. Okay, so for problem A, we are going to try and determine the Lewis structure first. So to do that, we want to get the total number of valence electrons, which in this it's 40. And then we're going to do the skeletal outline first. And to do that, we're going to look at the molecular formula. So we know that P is in the middle. We have 3 chlorines and 2 fluorines. Next, we will distribute the valence electrons. So if you look at the second picture I posted, it shows the electrons distributed around the molecules. Now, to determine the VSEPR formula, you're first going to identify the central atom, the number of atoms attached to the central atom, and the number of lone pairs present on the central atom. So for PCl3F2, the VSEPR formula will be AX5. I also drew out a picture of the structure of the trigonal bipyramidal shape. Also, the hybridization is sp3d, so that's how I figured out how to draw the trigonal bipyramidal. And then we're going to determine the bond angles. So we know that between the fluorine and chlorine, it's a 90-degree angle. Between the 2 chlorines, it's a 120-degree angle. And between the 2 fluorines, it's 180. Alright, so part B of problem number 16, we're going to do the same thing. First, we're going to find the total number of valence electrons, which are 32. Then we're going to draw the skeletal outline of SnF4 by looking at the molecular formula. So from that, we know that Sn is in the middle, and then you put the 4 fluorines on each side of Sn. Next, you'll distribute the valence electrons to each of the molecules. And then to determine the VSEPR formula, you'll identify the central atom again and the numbers of atoms attached to the central atom. Also, the number of lone pairs present in the central atom. So the VSEPR formula for SnF4 is AX4. To identify the molecular shape with the help of the VSEPR model, it's predicted to have a particular electron arrangement. So the hybridization is sp3, and then this shape is going to be tetrahedral. After determining the electronic arrangement and shape, the bond angles can be determined by the VSEPR model. So the bond angle in between the 2 bonds is 109.5 degrees. Okay, now we move on to part C of problem 16. Again, first we will find the total number of valence electrons. For the fluorine atom, there are 7 valence electrons, and the 2 negative charges contribute the additional 2 electrons. So therefore, we're going to have 48 valence electrons. To draw the skeletal outline of this molecule, we're going to look at the molecular formula, and from this molecular formula we can determine that Sn is in the middle, and then the 6 fluorine atoms will be directed around it. Now we distribute those valence electrons to this structure. All of the fluorine atoms get the 6 valence electrons. And then you can't forget to put the -2 charge on your Lewis structure. That's a big part of your Lewis structure. And And then the VSEPR formula would be AX6 in this case, where A is SN and the X6 is 6 atoms of fluorine, and there are no lone pairs present on the central atom. Then you identify the molecular shape with the help of the VSEPR model. This molecular shape is going to be an octahedral shape. And now going on to the bond angles, we're going to have angles between the two adjacent bonds, which is 90 degrees, and between the opposite bonds, which is 180 degrees. Now on to part D of problem 16. We are dealing with an iodine atom and 5 fluorine atoms. So to determine the total number of valence electrons, the iodine and fluorine atoms has 7. Therefore, the total is 6 times 7, which is 42 valence electrons. To draw the skeletal outline, so the Lewis structure, the first step of the Lewis structure, we'll look at its molecular formula again and know that iodine is the central atom and the fluorine atoms are distributed around iodine. Now we're going to distribute the valence electrons. So for this one, iodine is going to have a lone pair of electrons. So for the VSEPR formula, it's going to be AX5E, where A is iodine, X5 is 5 atoms of fluorine, and E is the one lone pair present on the central atom of iodine. And now for the molecular shape, it's square pyramidal. And to determine the bond angles, the angle is going to be between the two bonds, and it is, or the two bonds of fluorine, and it's 90 degrees. Okay, last part is part E of problem 16. Again, we're going to first determine the total valence electrons. Xenon atom has 8 and oxygen atom has 6. So the total would be 8 plus 4 times 6, which is 32 total valence electrons. For the Lewis structure, we're going to determine it by the molecular formula, knowing that our xenon atom is the central atom, and then the oxygen atoms are going to be distributed equally around xenon. So when distributing the valence electron in this molecule, it acquires stable octet configuration. The xenon atom has availability of d orbitals, so it can expand its octet hence, which means it's surrounded by 8 pair of electrons. So the Lewis structure is the second picture with the double bonds and the 4 electrons distributed around the oxygen. For the VSEPR formula, it's going to be 8x4, where AX4, where A is xenon, X4 is 4 atoms of oxygen, and there's no lone pairs present on the central atom, so that's how you're going to determine it. The shape of this is drawn as the third picture that I've listed, so second one on the bottom left. It is tetrahedral, and after determining the electronic arrangement and shape, the bond angles can be determined by the VSEPR model. So the two bonds, or the angle between the two bonds is going to be 109.5. So now on to problem number 18. Remember the question reads, predict the bond angles at the central atom of the following molecules and ions. So for part A, we have OF2. So in this picture here, I've named the shape, which is a tetrahedral arrangement with an angular shape. So first we have to draw the Lewis structure, and we know that we have 2 bond pairs and 2 lone pairs, which equal 2 single bonds. So this central bond angle is going to be slightly below 109.7, so I predicted it would be 107 degrees because a tetrahedral bond angle is usually 109, and it's a little bit less than that. Okay, so part B, we have chlorine 2 with a negative charge. This is also a tetrahedral arrangement with angular shape. We know that from the hybridization, which was sp to the third. So since we have 2 bond pairs and 2 lone pairs, we're going to have a single bond and a double bond with oxygen. And then predicting the angle shape, a normal tetrahedral angle is 109.5. So this one's going to be slightly less than that. So I named it at 105 degrees. Part C of problem 18 is pretty much exactly like the one that we just did. It's also a tetrahedral arrangement with angular shape. Since we have 2 bond pairs and 2 lone pairs again, we'll also have a single and double bond with oxygen. Knowing that this is a tetrahedral, we know that it's going to be 109.5, but I've named it slightly lower at 107 degrees. Alright, last part of problem 18, we have SeCl2, so the Lewis structure is going to be with Se in the middle and the 2 chlorines on the sides. This one is also tetrahedral arrangement with angular shape. We know that we have 2 bond pairs and 2 lone pairs. And in this one we're going to have 2 single bonds. And then this central bond angle between the 2 chlorines is going to be 103 degrees.